We've investigated the nature of magnetic fields, namely the fact that they put forces on moving charges. But now let's get a little more intimate with the magnetic fields and consider their sources, which will also lead to Ampere's law. Well, just a quick review. We know that a charge creates an electric field, which causes a force on another charge Q. Then we've recently learned that a magnetic field causes a force on a moving charge. So let's see, E field causes a force on a Q, but a Q is what creates the E field. A B field causes a force on a moving Q. I wonder if a moving Q creates a B field. Well, experiments demonstrate that in fact it does. Let's consider an experimental situation here where this nature of the magnetic field is revealed. So we have a plane, we have positive Q, we're going to have it moving at velocity v as shown, and we're going to consider observing the effects at point P, radius r, angle phi between v and that position. Well, the first thing we recognize is that an E field is produced, kq over r squared, 1 over 4 pi epsilon 0, q over r squared, the electric field. But, surprisingly, there's also a magnetic field, which can be measured to be acting in a direction perpendicular to the VR plane, and so it's pointing up here. And what is the size of that magnetic field? Well, it's got a constant, mu 0 over 4 pi, so let's not worry about that. But what is it proportional to? Things that you will not be too surprised to realize, namely the charge itself and how fast it's going, then modified by the angle, namely the sine of the angle. Oh, that tells you something about how this is going to vary with this angle, like if it's directly in line with it versus perpendicular to the velocity. So let's consider, oh, and very interesting, it's an inverse square law. But maybe that's not so surprising because it's from a point source. Well, let's consider other points on this plane, these points shown, and measure the magnetic field there and discover their relative sizes and directions. Let's start with this point over in the corner. And yes, this angle is 90 degrees, so it's larger there. Then it gets smaller as we progress around the circle. And then, on the other side, the magnetic field is oppositely oriented. And look at what happens here. Even bigger. We're closer. What do you think the magnetic field is here? Well, the sine of 0. Okay. Well, let's consider unit vector r. Remember what a unit vector is? A unit vector is just the vector itself divided by its magnitude, which makes it equal to 1. In a spatial, pointing in a spatial direction. All right. So we're left with a result that is a very fundamental equation of magnetism, namely a magnetic field produced by a moving charge is given as mu 0 over 4 pi qv cross r over r squared. It's an inverse square law that has all the relevant quantities embedded within it, and this, as I said, is a very fundamental force of equation of magnetism. Now, just to finish this, consider a little circular region around here that encompasses this point already. And what happens if we measure the magnetic field around? Well, just extrapolating from what we've already discussed, we should expect a magnetic field that is oriented geometrically like I'm showing here. Namely going down here, over to the right here, to the left over here, etc. So we notice there's kind of a circularity in the magnetic field in that spatial region, which is also consistent with the idea of magnetic fields not being monopoles, but forming enclosed loops. And again, this expresses the size of that magnetic field. Well, without any further ado, let's get a little more hands-on, and take the result of what we just discovered, or revisited from what others have done, and consider the magnetic field produced by a moving charge. So, we will use a right-hand rule, surprise, surprise. So you take this charge that's moving into the page, or the screen, grab that cue, with the thumb in the direction of the motion of the charge. The fingers, your fingers, will curl in the direction of the magnetic field. It's all at a constant speed. So, this is the direction that your fingers should be curling. So I'm drawing several magnetic field loops, and might kind of look similar to the equipotential lines we drew for charges. And there's it's equa-magnetic field lines, all right, in terms of magnitude at least. Now, what is mu zero? It's time to see the connection between this magnetic constant and bring in the permittivity constant as well. This is called the permeability, the ability for a magnetic field to exist in the medium we're discussing. Now, mu zero turns out to be exactly 4 pi times 10 to the negative 7. Seems a little strange, probably. And it's Webers per amp meter. But remember, a Weber is a Tesla meter squared. So this is Tesla meter over amps. Now, K, as we've learned before, is 1 over 4 pi epsilon 0. And epsilon 0 we have an exact quantity for, size for, that we basically approximate when we write it. But it's actually 1 over 4 pi epsilon 0 is 10 to the minus 7 c squared. Speed of light squared times 10 to the negative 7. You can put that exact number in the expressions for electric field forces and discover that that's true. Now, epsilon 0 then, if we solve it here, is simply 1 over 4 pi epsilon 1 over 4 pi times 10 to the negative 7 c squared. So let's bring that together with the permeability constant, the magnetic and electric constants. So we multiply them together, we get this, which gives us 1 over c squared. So we see a rather intimate connection between these magnetic and electric constants and the speed of light. Namely, the speed of light squared is 1 over mu 0 epsilon 0. Now that's pretty awesome and interesting, especially considering that electro, which is associated with permittivity, magnetic, associated with permeability, waves in a vacuum propagate, travel, move through the vacuum of space at velocity c. So, well, it turns out that Maxwell, James Clerk Maxwell, in the 1800s, actually predicted the speed of light before it was carefully measured. He predicted that based on these constants that emerged from his theories of electromagnetism. So that's a very fundamental, deeply interconnected reality, namely this electric and magnetic phenomena. And we will see more evidence of their interrelatedness as we progress forward. Magnetic fields are quite ubiquitous in our universe, from near at home to way out in space. Here we have the sun, lots of magnetic effects on the sun. So the sun is just a big ball of gas, mostly plasma, moving charges. Those moving charges are producing all sorts of magnetic loops on the sun. Not just limited to the sun, but beyond as well. Here, 1,500 light years away in the Orion Nebula, we have evidence for charged particles. And as these particles are moving, they produce these magnetic fields. The magnetic fields produce forces on charges. And so this significantly modifies the large-scale structures out there, which really are the structures that are producing solar systems like ours, producing rocky planets, producing bipedal primates, carbon-based, like you and me. So our lives are intimately connected to the production of magnetic fields. Isn't that a profound thought? Let's finish this introduction with an absolutely fantastic example that will really reveal a lot, bring it all together, what we knew and what we just learned. We're going to consider two protons moving in opposite directions at the same speed. So we have our reference frame spatially here. So they're separated by radius r. We're going to find the ratio of the forces of the electric and magnetic effects. That should be fun. All right, so first, the easy part. The electric force between these two charges, kq over r squared. I'm sorry, qq over r squared. And the q's are the same. So there it is. Now, that force is directed this way, just because, you know, opposites attract, likes repel. Now, the magnetic field, from what we just learned, we have this formula, this inverse square law formula from moving charges. We're going to consider, for the moment, the motion of one of the charges and its resulting magnetic field, which is then the magnetic field that the other charge feels or experiences. And then we have a charge moving in a magnetic field, which therefore experiences a force. So that's the direction we're going. Now when I say other right-hand rule, well, QV cross R. V cross R is a right-hand rule. So if you think of this motion with respect to this one, the V cross R, V is this way, and the radius is from here to here for the magnetic field produced by this charge. I'm sorry. This charge is moving to the right. Its radius is from its location to the other one. So what's the magnetic field produced at this location? So when we say V cross R, this V crossed into R. Take your right hand and swing V into R. Which direction is your thumb point? Well, it should point in the positive Z direction. So that's the direction of the magnetic field. Now the other thing we just learned is you have this charge moving to the right. Encircle that charge with your fingers, thumb pointing in the direction of V. Your fingers are encirculating the direction of the magnetic field. So as that circulates, you think of the expanding circles around there. Up here, it's coming around behind and coming out in the positive Z direction. Two right-hand rules will give you the same result. Now, the force on the upper charge from the bottom moving charge is QV cross B. And the only reason there's a force is because there is a B field from this guy at this location. And this one is moving. So QV cross B. That's the B field times QV. So everything is perpendicular. So we have QV over R squared and multiplied by Q and V. So Q squared V squared over R squared. So that's the size of the magnetic field. And we need to figure out, we've already figured out the direction of the field. Now what about the magnetic force? This way. Why is it that way? It's the QVB force. So VB, so take your right hand, swing V into B, and you get your thumb pointing upward. Or take your fingers and stick the fingers of your right hand in the direction of B with your thumb pointing this way. So you're pointing your fingers at your body right now with your hand twisted over, thumb pointing to the left, and your palm is pointing up. So it all works. So that's a lot put together there. Now what's the ratio of these two forces, FB over FE? Very simple. Mu 0 over 4 pi, Q squared V squared over R squared over 1 over 4 pi epsilon 0, Q squared over R squared. Let's cancel some stuff. Yeah, that's a lot of cancellation. Giving us mu 0 epsilon 0 v squared, and mu 0 epsilon 0 is 1 over c squared. So pretty amazingly, the ratio of the magnetic over the electric force is v squared over c squared, considering when v is much smaller than c, so we don't have relativistic effects. And they're in the same reference frame, which they are in this case. Puppy, what's up over there? You're disturbing the recording. So quiet down. There's no moose out there right now. If there is, I'd let you out and you could get a meal for yourself. Okay, so that'll conclude this introduction to the sources of magnetic fields and putting them together with the force effects resulting from moving charges, producing B fields, and subsequently influencing other charges.